Yes, before we begin, any questions? Yes, in rolling without slipping. At the bottom of this one. Okay. Can you speak a bit louder? VB prime is equal to V, this one. So here what we were doing is we were mainly dealing with two different reference frames. Now one of the reference frames was the one in which the wheel is moving with a speed V. The other reference frame is a reference frame which is also moving with the speed V, so the center of mass is at rest. Now in this reference frame in which the rotation axis is at rest, the bottom point is moving in this direction with speed V. The top point is moving in this direction with speed V. That is why we have these two things. So what we said was, you see, let's just look at in this reference frame, the wheel is rotating. We know that the speed at any point is nothing but the angular velocity times the distance from the rotation axis. So the speed of the top point, the speed of the bottom point, in fact, the speed of any point on this ring, they're all equal. So that's why we have here VB, VR, VT, VL, they're all equal. VL, VR, VT, VB, they're all equal to each other, and they're all equal to omega times R. So that is one thing. Now the other observation was that in the initial reference frame, in which the wheel is moving with velocity V, in this reference frame, we had discussed, although I couldn't convince at least one of you, that this point was at rest, and we can treat the motion of this object as if it is rotating around this axis, which is at rest. At this instant, it is as if it is rotating around this axis with the same angular velocity. Since the angular velocity is the same, we know that this point, the motion, the speed of this point is angular velocity times this distance. Angular speed times this distance, which is also omega r. So we know that VL, VR, VT, VB, they are all equal, and they are all equal to V, which is omega r over here. So these are the two reference frames that we are discussing. One is the relative to the reference frame of the axis of rotation, and the other one is the reference frame in which the wheel is rolling without slipping. Other questions? You will be having your midterm this weekend. Come on, that shouldn't be a surprise.
At some point you said derivative of angular momentum relative to time and gives torque.
Yes.
You mentioned there are cases that it's not relative. The axis is not.
Now, you see, this is always valid. Torque is always equal to dl by dt. This is always true. What is not always true is that this is always. L is equal to I omega. This is not always, or let's say almost always. This is not always true. And we even discussed one case in which it is not actually true. We have this rod. If it rotates like this, in that case, its angular momentum is not in the same. I mean, this equation tells us that the angular momentum and the angular velocity vector, they are in the same direction. They don't have to be. No. We are not free to choose the direction of omega. The direction of omega is already fixed. The direct omega, you see, omega should satisfy this one. This is the velocity of the axis. R is the distance to the axis. And V is the velocity of a rigid body, of a point on the rigid body. You cannot choose omega freely. Even that is not true. Omega is the same for all the axes that we choose. The rotation axis, I mean the direction of the rotation axis is fixed. We cannot change that. True. True. Well, let's see what happens if we change the point. Now, your friend is saying that, okay, so let's just take this three-dimensional object. Let's say this one. Okay? This is our axis. Let's say we choose the z-axis to be our rotation axis. And we are calculating the angular momentum with respect to the origin. That's what we usually do. And in fact, we said that, usually we first choose our axis, the coordinate axis, then we choose the rotation axis, etc. Now we can also, let's say, if we move our origin, let's say, along the angular velocity, how does the angular momentum change? So let's see. We had defined L as Ri cross Pi. So we just divide our object into small bits. And for each bit, Ri is the position relative to this point. Let's say this is the vector D. Ri is, let's say, relative to this point. Pi is the linear momentum. Now, if relative to the point A, LA, this is the angular momentum. To the point A. In fact, in this case, I just assume D to be along omega, but we will see if it is necessary or not. Let's see how the angular momentum changes if I shift my reference point. Now, in that case, LA will be equal to, let's say this is the point of Ri. Now I need this point, this Ri prime, the position of my object relative to my new reference point. But I know that here I have these three vectors. I know from vector addition that Ri prime plus D is nothing but Ri. So let's see, even before this, let's see what L is. L will be equal to Ri is D plus Ri prime cross Pi. This is equal to D cross sum of Pi plus Ri prime cross pi. I'm just shifting my vector origins, and this is how the angular momentum is modified. This quantity over here is nothing but the angular momentum relative to A. L is equal to LA plus D cross pi, or LA plus D cross the total momentum of my system. D is the vector or the center of mass connecting the two reference points. Okay, so what does this tell us? Now your comment was that, okay, we were defining angular velocity relative to an axis and angular momentum relative to a reference point. Now let's say one question might be, can we choose our reference point such that this is parallel to the angular velocity? Would it be possible? So the question is it possible to omega? Can we always choose such an axis? So what we do to test that? How do you test that two vectors are parallel to each other? Vectoral product is 0. Suppose it is possible. If possible, then omega cross LA should be equal to 0. Suppose you choose one reference point. You choose one reference point, and then you calculate the angular momentum relative to that reference point. That is what you get, L. Then you want to find this point A or this vector D such that LA would be parallel to omega. That's what we are trying to do now. Now let's just take use this cross product. Take the cross product of this expression with respect to W. W cross L should be equal to W cross D cross P, center of mass. So if this equation has a solution, then there exists a point A such that LA is equal to I. Of course, this time it's the moment of inertia around the axis A times omega. Okay, it might exist such a point. So in a sense, you are right. I mean, we have this kind of freedom to choose, and we can choose a point such that the angular momentum can be parallel to omega, but we don't have to. So depending on the problem, maybe that this point is not such a suitable point. True. You see, angular momentum always, before when we were talking about the velocities, we always said that velocity depends on your reference frame. So if you change your reference frame, then the velocities change. In the case of the angular momentum, it's not even the reference frame, but if you change your reference point, you can say that, okay, you have two reference frames that are at rest relative to each other, they just have a different origin, and you are calculating the angular momentum always relative to the origin. Even if they are not moving, you will be measuring the same velocities in both of the reference frames. You can still measure the different angular momentum because this vector R will be different. If you take two different coordinate axes which are not moving relative to each other, so the momentum of all the particles are the same for both of them, but nevertheless their position vector will be different, and hence their angular momentum will be different in different reference frames. Not even reference frames, if you just take different origins.
In these vector products, how can we decide the order of the quantities?
The ordering.
I mean, R products P or P products R.
This is the definition.
R is always
In the definition of the angular momentum, R is always the first one.
and in the other cases.
In the torque also, you see these are the definitions.
Yeah. R is always first.
There is no such rule as R comes the first. Just remember the definitions. The definitions includes in which way you should order them. Don't worry, all these formulas you have in your midterm. In the first sheet, there is the formula sheet. You have all these orderings. So you don't have to memorize this. Other questions? Now today there are two examples that I would like to discuss. One is this one. Let's start with this one. So just imagine that this is an air table, there is no friction whatsoever. There is one rod lying over there on the frictionless surface at rest. And then you send your puck at 90 degrees to this rod. And then they stick together. And once they stick together, if you just take a rod, hit it from one end, you know that it will be rotating and also it will be translating. So what will be the angular velocity? What will be the velocity of the center of mass, etc.? No, they are free. There is no force whatsoever acting on any one of them, except on the force that they exert on each other. So this rod is free to move. This is just frictionlessly moving. They just stick together. Now, conservation laws are there to help us. So if we can use the conservation laws, then that's great, that they will simplify our lives. So what are the conservation laws that we had studied until now? We have the energy conservation, momentum conservation, and angular momentum conservation. So let's see if any one of them would be conserved or not. Is energy conserved? Why not? It's an elastic collision. So the energy is not conserved. Is linear momentum conserved? Why? The system is isolated. You see, the linear momentum, the total momentum of a system changes only if there is an external force acting on the system. If you look at this system, the momentum of this ball is not conserved, it changes. The momentum of this rod is not conserved, it changes because the ball is exerting a force on the rod. Similarly, the rod is exerting a force on this mass, M. But if we consider the whole system, there is no external force. All the forces that we said are internal forces. So the total momentum, the momentum of this mass plus the momentum of the rod, is conserved. This is conserved. Is the linear momentum conserved? Sorry, the angular momentum conserved. You see, the rate of change of angular momentum is given by the external torque acting on the system. Is there an external torque acting on my system? There is no external torque acting on my system, so angular momentum is conserved. Now, as your friend has pointed out, I mean, it could have been that we just fix this point by a nail, we let it to rotate freely, but it cannot move. That's also a valid question. Well, in that case, the linear momentum wouldn't be conserved, because here we have a force acting on the system, an external force acting on the system. If we had attached this by a nail, then that would exert a force to keep this point fixed, and hence linear momentum wouldn't have been conserved. Now, the angular momentum, would it have been conserved if there was a nail over here which would allow it to rotate but not move? If we put a nail over here. Good question. If somebody asks you, is angular momentum conserved, the first thing that you should think is relative to which point? Now, before, when there's no nail over here, we didn't consider that because there's no external force anyway. Since there's no external force, relative to any point, there are no external torques. But now we have an external force. So if you try to calculate, I don't know, the angular momentum relative to this point, if this is fixed, if it was fixed, then relative to that point, it's likely that we would get a torque created by the force over here. So the angular momentum relative to that point will not be conserved. But angular momentum relative to this point, let's say A, would have been conserved because there is a force acting on my mass at this point, but that force I don't know how much, in which direction, but still I know that it's acting on this point, so it doesn't create any torque relative to this point. So the angular momentum relative to this point would have been conserved, although linear momentum wouldn't be conserved. And linear momentum wouldn't be conserved, angular momentum relative to arbitrary point wouldn't be conserved, but angular momentum relative to this point would be conserved. Anyway, so, yes.
Hocam şimdi o A noktasını biz neden sistemin dışına koyuyoruz? Hepsini üçünü beraber bir sistem olarak kabul ediyoruz.
You see, this A point is connected to Earth. So if you want to consider the free body system, the mass, the rod, and the Earth, of course the angular momentum would still be conserved. But we don't know what the Earth is doing. We wouldn't like to deal with Earth. So
Sana böyle bir soruyla karşılaştığım zaman soruda bunun sistemin dışında olduğu yazması gerekmiyor mu? Yoksa ben sistem olarak kabul ediyorum.
You see, in the question, or just imagine in real life, when you see such a system, nobody is telling you that you should take this as your system. Nobody is telling you that. You should determine which system you are studying. As I said, you can look at this single mass M. You can say that that is one system, the rod is another system, the Earth is my third system. You can try to attack the problem from that point of view. You will get a hard life. You can still do that. Or you can prefer to choose the mass, the rod, and the Earth as your system. That is also valid. And as long as you do the correct things, you might be able to get a final result. But again, it will be quite complicated. Or you can say that the mass and the rod is my full system. And then in such a choice, the choice is yours. You have to make that choice. This choice would make your life easier. That is part of the thing that you need to learn. We have been discussing all these freedoms, like you are free to choose your reference frames, whichever frame you want. You will be choosing them. You will not be told which one to use in nature when you try to explain nature. Nature won't come up with a solutions manual. So you will not know. You have to choose. Just like here, you have to choose which momentum you should consider, which energy, which angular momentum to be considered. Okay, back to our problem. This one. The rod is free to move. The mass comes and hits the rod at the top. and the system sticks together and they just roll and make translational motion, etc. In this system, the linear momentum and the angular momentum, they are both conserved. So let's start with what the velocity of the center of mass. We had defined the velocity of the center of mass as the total momentum was defined as the total mass of my system times the velocity of the center of mass. This should be equal to, let's put our axis, x, y, and z. Z is pointing towards you. Let me, just for computational simplicity, let me assume that they are both have the same mass. So this is the total momentum is the total mass times the velocity of the center of mass. This should be equal to, well, what is the total momentum of my system? What is the momentum of this mass? M times V. What is the momentum, initial momentum of the rod? It is 0. So this tells me that the velocity of the center of mass is V over 2. This is true before the collision. This is true after the collision. Since the velocity, since there are no external forces, the velocity of the center of mass does not change. So this is what the conservation of linear momentum tells me. So we had already used that. Let's look at the conservation of the angular momentum. Now we should first write down the initial angular momentum, the final angular momentum, and just equate them to each other. So with respect to which point would you like to write down the angular momentum? Center of the rod. Center of the bottom of the rod. Okay. Let's just give it. Let's try all of them, as much as we have time. Let's start with the center of the rod. Let me just give some names. This point A. This point, let's say B. Maybe this point C. This point D. I will start from A, then go to D. There's a reason why I chose the D, and then we will see how much time we have. The angular momentum relative to A, initially. What is the angular momentum relative to A? Remember, the angular momentum is always R cross P. For a point object. So let's look at initially R, in this case would be, let's calculate what is the angular momentum of this rod relative to the point, initial angular momentum of the rod. It is 0. There is no angular momentum relative. It's not moving, it's not rotating, so there is no angular momentum. What is the angular? So the initial angular momentum is completely due to this mass. What is the angular momentum of that mass? What is the direction of the angular momentum? So let's say this is R. So what is the direction? Inside. Inside. So I say this is R. P is in this direction, R cross P, just take your right hand, curl your fingers, it is into the screen. So angular momentum, initial angular momentum is definitely in the minus Z direction. It is in the minus Z direction. What about the magnitude? Well, let's say our definition was R times mv times sine of the angle between the two. This is our definition. Now the sine of between the two is this angle. This is our theta. Now if that is theta, this is pi minus theta. So this is equal to, in the minus z hat direction, mvr sine of pi minus theta. R times sine pi minus theta is nothing but this length over here. So it's L over 2. This is the initial angular momentum relative to the point A. Now we say if you look at this expression, R changes with time. That is the distance from the point A. As the mass is moving towards the rod, as this mass is moving, this distance is constantly changing. Similarly, this angle is constantly changing. It started from, at infinity, it was almost 180 degrees. And as it comes to this point, it's 90 degrees. As it goes to plus infinity, if it would go to plus infinity, it would become 0. So it's a time-dependent function. That's theta. R is time-dependent. But R times sine theta is just L over 2. That is a constant. So this is the initial. Now let's look at the final angular momentum. Relative to the point A. Remember, again, this would be, now finally, okay, you see, once you choose the reference point, it stays there. It doesn't move with your object. So as my object is rolling now, my point A is still somewhere over here. That didn't change. Okay, that is something to keep in mind. So this is still, after the collision, this is still my point A. So it didn't start moving with the rod, it is fixed. Now it is doing, there is this complicated object which is doing translational and rotational motion. So there is no fixed axis, there is no just point mass moving around. So the easiest choice would be just to use the fact that we can always separate the angular momentum as the angular momentum of the center of mass plus the angular momentum relative to the center of mass. This separation we can always do. Now, where is the center of mass of this object, of this system as a whole? The center of mass is not at D.
After collision.
Well, the center of mass has a velocity, so it is always moving. So we can say that, okay, this is not such a great drawing, but let's say that these just overlap. Now the center of mass is somewhere over here. This is the center of mass. You see, at the moment that this mass M hits this rod, at that instant, before the rod has been displaced, before it covered any distance, this is the position of the center of mass. And we know that the center of mass, the velocity of the center of mass is constant. So the center of mass is just doing motion with constant velocity. So it's basically going on a straight line. So that's why I just moved it over here. This is the trace of the trajectory of the center of mass. That horizontal line is the trajectory of my center of mass. So that point will always, this point D will always stay on this line as the rod is moving and rolling. Now there are two things we have to do. First of all, still we are calculating the moment of inertia relative to the point A. So the angular momentum relative to the point A. So this is our center of mass at this instant. This is P, center of mass, the total momentum of my system. So what is the direction of R cross P? Into the screen, out of the screen. Let's see. This is R. This is P. R cross P. Just imagine R is rotating towards P. R cross P, it's still into the screen. So it's in the minus Z direction. This is equal in the minus Z direction. R cross P, if you remember the definition of the cross product, it is our center of mass, the distance of the center of mass, times 2m times V. This is the total momentum of my system. No, sorry, m times V. Here I already used the momentum conservation. Times sine of, let's say, phi. This angle here is the angle phi. Or this angle over here is the angle phi. Now we see this length times sine of phi is nothing but this distance over here. This distance is our center of mass times sine of phi. So what is that distance? L over 4. You see, since both have the same mass, the center of mass of the rod and the center of mass of this point mass is just, if you connect them by a line, it's just at the middle of that line. So it's right this point or this point is at the middle, both vertically at the middle and horizontally at the middle. So vertically at the middle is this point D, which is at a distance L over 4 from the center. So this minus Z hat mv L over 4. This is only due to the translational motion of the center of mass. Plus, of course, we have the rotational motion. And for the rotational motion, we have the moment of inertia of my system as a whole through the center of mass times omega. Plus I, center of mass. What is the direction of omega? Well, let's say we don't know. Let's just assume we don't know the direction of omega. So let's just say it's omega in the z direction. It's in the z direction. This omega can be both positive or negative. We don't know for the time being. Now we know that the angular momentum is conserved. So this should be equal to the initial angular momentum. So minus z hat mv L over 2. This one should be equal to minus z hat mv L over 4 plus I center of mass omega final z hat. And from which we can determine omega final will be equal to minus 3 over 4 mvl over I center of mass. Okay, if the final angular velocity is a negative number, that tells me that the angular velocity of the final system is in the minus z direction. And if it is in the minus z direction, it just tells me that my system as a whole is rotating in the clockwise sense. So it is rotating like this. That is the clockwise sense, so that the final omega is in the minus z direction. There is still one last thing that we have to do. What is this I center of mass? So we have this object, this rod, and at the end we have a mass m. The rod has a length L, a total mass m. Now we had already calculated the moment of inertia of the rod relative to rotations around this point. Relative to the tip, we had calculated it to be 1 over 12 ml squared. This we know. Also in the exam, unless I'm asking you to calculate the moment of inertia, I will let you know at least one moment of inertia using which you can calculate. That was, no, that 1 over 3, you're right. This is we know, it was 1 over 3. And now, this is for a single rod. Here we don't have a rod, we have a rod plus a mass attached at the one point at the tip, and we want to find the moment of inertia for rotations around the center of mass, which is at a distance L over 4 from the tip. So the moment of inertia of the system as a whole for rotations around the center of mass will be, first we have, we will use the parallel axis theory. So we can say that this is I rho plus m times L over 4 squared. This is the moment of inertia of the point mass. Now, what is the moment of inertia of the rod for rotations around this point? How can we calculate that? Now, we will be using the parallel axis theorem, but let me ask you this one. I rod, is it equal to 1 over 3 ml squared? This moment of inertia we already know. Plus, we know the parallel axis theorem. The rod has a total mass m, and we are shifting it by L over 4. So is this true? Is this the parallel axis theorem? No. Your friend is right. To use the moment of inertia, the parallel axis theorem, we can only shift the moment of inertia for rotations around the center of mass of the rod. So what we want to calculate over here, I rod, is the moment of inertia. This is what we are interested in. I rod for rotations around this point, I say A. No, not A. Around A, we already know, or C. This, we were already given that it is equal to 1 over 3 ml squared. We want the moment of inertia for rotations around this point T. This is equal to, this was the point A, A is the center of mass of the rod. So the moment of inertia for rotation around this point D is IA plus m L over 4 squared. This distance is also L over 4. We also know one more thing, again due to the parallel axis theorem. The moment of inertia of the rod parallel for rotations around the point C is IA plus ml squared, ml over 2 squared. This is parallel axis theorem applied to the point C. We are shifting the center of mass by a distance L over 2. Well, this tells me that since I know the moment of inertia for rotations around the point C, 1 over 3 ml squared minus 1 over 4 ml squared is equal to IA. This is 1 over 12 ml squared. So this tells me what is the moment of inertia for rotation of the rod for rotation around its own center of mass. Now we have to shift it to D. ID of rod is equal to 1 over 12 ml squared plus ml squared over 16. This is 5 over 32 ml squared. So this is the moment of inertia of this rod for rotations around this point. Now we can go back to our initial problem. The whole system is rotating around this point. The rod is rotating around that point. The point mass is rotating around that point. So the moment of inertia of the whole system is just the sum of the moment of inertia of each one of them. We already knew the moment of inertia of the point mass. Now we also know this one. This is not I center of mass is equal to 5 over 32 ml squared plus 1 over 16 ml squared. This is 7 over 32 ml squared. This is the moment of inertia of the whole system for rotations around this point. Now we already had calculated the final velocity, angular velocity in terms of the moment of inertia around the center of mass. So this is equal to minus 3 over 4 mvl times 32 over 7 ml squared. Here. Where? Here. Why? This is 3 over, 30, sorry, you are right. It's 48,437. So this is 7 over 48. Over 48. Okay. 48 over 10 times 1 over ml squared. Now we are done because we have expressed everything in terms of the given parameters. Of course, you can simplify this 4 and 48 will give me 12. 18 over 5. V over L. So if we just go over what we had done. So the first step was identify what are conserved. I mean, some conservation law, in this problem, the conservations were obvious. In some cases, it will not be so obvious. Just don't go blindly that, okay, momentum is conserved. If you think that momentum is conserved, then you should know why it is conserved. Now, in this case, the linear momentum is conserved because there are no external forces acting on my system. And since there are no external forces acting on my system, the torque, external torque is 0. So the momentum and angular momentum, they are both conserved. Since they are both conserved, we first use the conservation of linear momentum. Okay, this is the definition of the center of mass. This is the total mass times the velocity of the center of mass. This is the total momentum, and hence we saw that the velocity of the center of mass is nothing but half the velocity of our point mass. This is true before the collision. This is the velocity of the center of mass after the collision. Because during the collision, velocity of the center of mass does not change. So this was part of the step, part of the solution. Now the next thing was the angular momentum. We know the angular momentum is conserved. But first we have to choose some reference point with respect to which to calculate the angular momentum. Now in this question, you preferred to calculate the angular momentum relative to this point. That is fine. And so we wrote down the initial angular momentum, which was just only due to this moving mass. Well, the calculation of the final angular momentum was kind of complicated, but we had to first separate it into two parts. The angular momentum due to the translational motion of the center of mass, plus the angular momentum due to the rotations around the center of mass. And we had to calculate each one of them separately. Now, one problem over here was to obtain the rotation of the center of mass, the angular momentum due to the rotation around the center of mass. To calculate that, we need the moment of inertia relative to the center of mass of the system. And in that case, we had to go through all this discussion about the parallel axis theorem, etc. But once we obtain this quantity, then the rest was just equating the initial angular momentum to the final angular momentum. The only unknown was the final angular velocity, and we could solve for the final angular velocity. An alternative choice. Okay, the reason why I would have preferred the point D was that relative to the point D, the center of mass is always at rest. The center of mass is moving, but the R cross P relative to this point, especially after the collision, is 0. So we wouldn't get the R cross P term. Now, relative to the point D, this term would have been absent. So it would slightly simplify the calculations a bit. But one thing is, it's kind of unavoidable to calculate this moment of inertia. Now, any questions on this one?
If you are moving reference frame, for example, if you use the center of mass every time you move, what correction do we need? And what correction do we need to obtain the same result?
I mean, you see, the angular velocity is kind of independent of your reference frame also. As long as you are in an inertial reference frame, the angular velocity would be the same.
I'm saying, while calculating angular momentum,
Okay,
we choose one point, for example, A.
sure.
If A was moving,
No, you see, you first choose your point, reference point. It should be fixed. The angular momentum is always calculated relative to a fixed point. Your reference points are always fixed. They don't change. You shouldn't change them during the motion. That's why I was stressing that this point A is always over there. It stays over there. If you want to go to another reference frame, let's say you want to go to another reference frame in which the center of mass is at rest, in that new reference frame, the point A wouldn't be fixed, it will be moving, but in that case, you are not allowed to use that point A, you should choose some other point which is fixed in your reference frame. You shouldn't complicate your life more than it really is. It already is. Well, I said that when I'm writing my equations, here I said that let omega be omega in the z direction. This omega is not the magnitude, it's the component in the positive z direction. So it just turned out to be, this number just turned out to be 0, so this number over here is minus, which just told me that it is rotating in the clockwise sense. So before solving, I don't even need to make any assumption on the direction of rotation. I can just leave it as arbitrary. The sign of this one can be arbitrary. Other questions? Okay, let's go for a 10-minute break.